Okay, we're going to get started. Holy cow, I can't see anything back there. These lights are bright. Okay, really quick exercise. I'm going to do my best to see, but I need some help from the audience. Can you raise your hand if you have ever had a GPU fall off the bus? I can't really see. I see a few.
There are some hands, yeah.
All right, keep your hands raised for a second. If you have had to restart a machine because a GPU wasn't working the way you'd hoped. How many more hands? Oh, even more. Okay, quite a few. Okay, you can put your hands down. Thank you. Okay, so we're from NVIDIA. I'm Ryan Hallisey. This is Natalie Bandel, and we encountered this too. I had my hand raised. She had her hand raised. We experienced this a lot. So we feel your pain on this. This is something that we're going to be talking about, how we deal with this. We run Kubernetes clusters, and we have a lot of GPUs, and we go through the same thing. We will reboot our GPUs for different various reasons. So that's what we're going to talk about. Okay, so a little bit about our Kubernetes clusters. We've got a large fleet. We've got geolocated all over the world, so pretty much we're in a lot of countries. 40 plus clusters, 30,000 plus nodes, 60,000 plus GPUs, so roughly two GPUs per node of density. And like I said, we run into a lot of device failures, so that's a lot of GPUs. So we do encounter this. Okay, so the product that we actually represent, we build the infrastructure for, it's called GeForce Now. It's, think, NVIDIA Cloud Gaming. So we want to take graphics and we want to stream these to the end user. So we want low latency, we're geolocated right near the user. And we want to give that desktop experience for the GPU, like you're playing the game locally. So our workload, primarily when representing and working with GeForce Now, is we have a lot of online gaming, like I said, and we also do a bit of inferencing. We have spot capacity, so we'll run some inferencing workloads there with our additional capacity. So we'll fill our data centers quite a bit. Okay, so device failures. So we want to maintain our capacity, right? It's really important. We want our GPUs running really hot. It costs us a lot of money. We put a lot of effort into putting them into the data center, and we want them used. So that's a really important thing, and thing that we're going to be thinking about a lot. So we really care about this, right? A device, we put all that effort into getting it into the data center, and we want it to run all the time. We want it to have lots of workloads on it. We want to make the user happy, right? So this is really important. So we want to run at maximum capacity all the time. Okay, so let's get into the device failures. There's a whole list here. There's probably, you've probably encountered at least one or multiple of these. So this is, so I asked you first about GPUs falling off the bus. So the little context about that. In the kernel ring buffer, there's a message. If you look when you're experiencing this type of failure, there'll be a message that's saying that your device has fallen off the bus. And so how does that happen? Well, these are all the things that can lead to that. So I'll go into like maybe a few of these. So overheating. GPUs, we know, they use a lot of power. So what are lots of ways that we can cause problems? Well, we can use them a ton. They could overheat, and this could lead to a GPU falling off the bus. Insufficient power supply. Think of the amount of wattage and that is being transferred over the copper, right? We need to be really careful about how much, like how the connections are, like they're really closely, or like the copper is like whatever the perfect quality, and the leads are touching, and all the different things you can imagine that could possibly go wrong with power transferring over wire. Any of that stuff could possibly cause this error. And then the third one I'll go into, this will be the last one, will be driver failures, driver issues. We experience this a lot. We run KubeVirt, we run a lot of VMs. Our workload runs in VMs. So what we do is we'll launch a virtual machine, and we'll pass through the GPU. And to do that, you have to use the VFIO driver. And we will also use media devices. So we will use vGPUs, which means we need to use the NVIDIA driver. So we're constantly changing our driver on the fly, and sometimes we run into issues where we change the driver and it doesn't quite work, and we run into some sort of failure. So in all cases, or almost all these cases, we have to deal with it in some way. Okay, and so here's actually a picture of an example of the message. The GPU has fallen off the bus. So when we actually started our journey, when we were looking at trying to understand and achieve that goal of having maximum capacity, we needed to understand. We ran into some problems. We wanted to understand that why some nodes weren't quite filling up, and this was something that we noticed. And sometimes we would go to the node and we see workloads aren't running there, and we discover eventually these kinds of issues are happening. So we needed to do some work. We needed to discover what is going on, and eventually this discovery led us to here, which is what Natalie's going to go into more detail about in just a second. Different ways of how we dealt with these GPU failures so that we can make sure we're maximizing our capacity. Okay, so just to give you a picture of what I'm talking about when I say we've been experiencing device failure. So for numbers here, I said 60,000 GPUs, 30,000 plus nodes, 40 plus clusters. So here's roughly in a timeline what we experience. And this varies a little bit based on various things like drivers and a bunch of other things that can change these numbers a little bit. So roughly what I'd say is between like 120 and 190 or maybe 200 we'll experience between 120 and 200 GPU failures over a 24-hour period. So it's quite a bit, 120 to 200, somewhere in that range. And so what happens? We have to do something about that, right? That's a lot of devices that we now have to fix. We need to reboot the machine, right? Or whatever it is that we need to do to fix it. So Natalie's going to talk through some of the tools and techniques that helped us get through this so that we're not constantly getting paged to go in and fix things, and what automation tools and techniques that we did to actually deal with this so that we can run at maximum capacity.
Let me take you through what we are doing to make sure our GPUs and devices are at max capacity. So the first step to solve the problem is to acknowledge the problem exists. It's not always trivial, right? Our discovery mechanism has two parts. First part is custom GPU problem detector, and we use an internal GPU device plugin. It extends the GPU device plugin framework to detect driver failures. When it detects the problem, it marks the node and puts in a condition on the node. And then our second part of the solution kicks in. That's node problem detector. It's an open source project, and it goes over all the nodes and looks which nodes were marked. And those nodes that are marked are being sent into a remediation process. Once the remediation process kicks in, we have the built-in solution that takes and has maintenance going over the node, and we can automate that and monitor that process. We actually talked about it in last KubeCon. Ryan had a talk that is called "All Your GPUs Belong to Us." I will add a QR code with a link to the slides later if you want to go and check that one out. So now that we know how to discover those failures and how to take the node and do something to return this GPU capacity back, let's talk a little bit what exactly do we do. In the next slides, we talk how we try to solve this problem. and how we try to bring the node capacity back into the functioning state. So you might think that reboot everything is a joke. No, actually, it's the strategy. Reboot solves our problems. It has short downtime if there's no workloads on the node. It resets the driver. We get a fresh state on the node, and it basically works. Oops. But, of course, reboot has some downsides, especially if the node has workloads running on it. We have to either migrate the workloads or wait for them to finish. Node drain is the most time-consuming part. So let's see how much time-consuming that actually is. As Ryan mentioned, we have many, many clusters. So we wanted to make a Grafana dashboard that shows how long it takes to drain a node. We accumulated data over a period of several weeks, and each row represents a different cluster. Each column is how long it took for nodes to drain. So we can see that many nodes drain within an hour, but there are a long tail of nodes. And for some of them, it can take even up to 8 hours, especially if you have long-running workloads. And as one of the keynote sessions today stated, the cloud and your money is not infinite, right? We want those nodes with the GPUs to be available. We want to use them as much as possible. So this is our solution to device failure problem. We discover the failures, we drain the nodes, and reboot. And we do it in an endless loop on all of our clusters. Our journey started mostly with manual steps. And we were looking at Grafana dashboards, saw nodes that didn't have workloads, went to the node and manually cordoned it, labeled as broken, and later rebooted it. The process was time and effort consuming. The response was not fast enough, and of course it didn't scale. So we created automation and some improvements around all these areas, and now we're going to talk about some of them. With these improvements and automation, we can get much closer to the max capacity. Our improvements touched several areas, such as monitoring, node drain, and the reboot that we already mentioned. So let's talk about each. For the monitoring, we often had a situation when we were fixing the same node over and over again. To solve this problem, we've added this alert to detect such remediation loops, meaning that when node gets rebooted many times over and over again. This specific alert that we've added, it goes and checks if the node went into a reboot more than twice over 90 minutes, the alert fires, and we look at the node. No point of trying to reboot such node again if previous couple of reboots didn't solve the problem. After the discovery of this node that requires a reboot, we are scheduling them to drain. And we saw that drain can be a potentially really painful process. So is there anything we can do to speed it up? I mean, except for killing the sessions, which we would never do that, right? So we thought about two things, and we implemented them. First, we integrated with our tenant to drain spot capacity and pre-warm sessions. We also prioritized those nodes over other less urgent maintenance activities in the cluster. It means if we need to reboot a node because there's a device failure, we try to do that as soon as possible. We don't always have enough capacity to do it immediately, but we prioritize that. After the node is drained and there are no workloads, we can finally reboot it to get the GPUs and the devices back working. Reboot doesn't always solve our problem. Sometimes there are more steps we need to take. So we created this recovery workflow that you see on the slide. And it goes through reboot, then power cycle, then rebuild, and if that doesn't help, we have a manual intervention and RMA. We automated some of that, and some of that is still manual. But for example, when there is a remediation loop discovered, it means that several reboots didn't help. We automatically mark that node to go into rebuild process. And we have a automated rebuild process that runs periodically and discovers those nodes, and then it can automatically rebuild them. We still have some challenges that we look into solving in the future. For example, we would really love to know that after reboot or power cycle or whatever step we took, we bring back the node into the cluster and we know that the problem is solved. Right now, we know that the problem is solved only after the node is back in cluster and we run some workloads on it. So we talked about 3 steps for fixing our GPUs, that sometimes they have the tendency to fall off the bus. And this slide talks about how we try to keep the GPUs on the bus as long as possible and without reboots. We try to do that with several things. First, we monitor the GPU health. We have Grafana dashboards, and we have alerts for GPU metrics, such as temperature, anomalies, power usage, and so on. This might help prevent problems with what Ryan mentioned earlier about overheating and power issues and things like that. From the node perspective, we use Node Problem Detector to catch kernel issues and system errors and more things like that. We do periodic proactive self-tests on nodes and on GPU. And to prevent scheduling workloads on unhealthy nodes, we use some taints and tolerations. If we know that we will need to drain the node soon, we might not allow workflows on that node as soon as possible. Our process for maintenance and upgrades includes automatic sanity tests. And those tests have workloads to verify that the node and the GPU are still healthy. So for each maintenance or upgrade that we do on a node, we run some sanity after that. This way, we know that we did not break the node or the devices on the node because of driver failures or some incompatibilities. Of course, we regularly update drivers, Kubernetes components, operating system, and on the node, and so on. For that part, we have created a solution that is called Pika, and it is open sourced starting a couple of months ago. And you're welcome to take a look at it. I will also add the link to that in the slides later after. So our goal is basically to keep the devices healthy and maximize their uptime. We try to do that by preventing issues, and when there is a problem, we drain the node and schedule it into the recovery workflow. But we should not forget that reboot has a cost. And the cost is the entire node downtime and the node drain time. And we saw it might take a while, right? Currently, there are nodes with 2 to 4 GPUs, and that's the typical configuration in large data centers. But there is a notable trend towards configuring nodes with up to 8 GPUs, particularly to meet the demands of AI workloads. And as the number of GPUs on the node increases, so does the cost of the node's reboot. We are facing some new challenges here, and we want to figure out mostly how we can use Kubernetes. How can Kubernetes help us here to solve those challenges with looking forward to increasing the GPU capacity per node? For example, can we leverage the schedule? Can the schedule move workloads away from a node when one GPU is failing? Or can the schedule detect a node that is being rebooted every couple of days? Those are questions and challenges that we start to think about. And we start to think forward how we can get help from Kubernetes on these challenges, how we can raise awareness in the community about these challenges, and how we can work together to solve those eventually.
So like Natalie mentioned, which is like really interesting to think about. So we get to 8 GPUs, right? We can get to 16 GPUs, and then you also think about what happens when we have these long-running, really big machine learning workflows that are now going to have multiple GPUs, and they're going to be across different nodes, right? Are we going to be rebooting all sorts of nodes, and how is that going to affect our clusters? Like how can we think about that? So what I wanted to share with everyone is so I started a working group with Red Hat. This is Philippe from Red Hat. We just proposed this. It's called Node Lifecycle. And what we're looking to do is to work with the community, work with all of you to figure out this problem, to see how we can use Kubernetes to help us, particularly in the areas where we feel like this problem has caused a lot of people to build different solutions on their own. I've heard personally from a lot of different people who have already done that, and we've even done it ourselves, like we just talked through. And we really think that these problems many of them can be solved together in the community. And so that's what we want to address here in this working group that we've proposed. And so we're looking for your support. So, for everyone, that's interested, please come check out the link. Tell us about your use cases. Tell us about things that you would want to have to help you do maintenance inside of your Kubernetes clusters. You can come find us afterwards. We're also on Slack. And like I said, please comment on the pull request. We want to build this charter so that it can be effective, for helping you do maintenance and all the different challenges that come with the day 2 device management. Okay, with that, we'll open it up for questions. Thank you.
This is the feedback QR code. I would appreciate any feedback you have.
Hey, thanks for the talk. As we've come to these challenges too, we see that you use the node problem detector, and as far as we've been looking at it, it doesn't have any GPU support for detecting the problems. Any plans to open source or share with the community? How do you do that so we can also reuse it?
Yeah, I think that's a good question. I think we could certainly do it. I think I just think it hasn't been on a roadmap, but we could certainly prioritize and get that. shared. I think the only thing, though, I believe we would have to create a plugin or something. Is that how it would work? I think, but we would have to figure that out. Maybe we can have something in. We could find a place for it so that everyone out there can do exactly what we're doing. So we can look into it. I'd be happy to look into that, and we can find a way to do it.
Awesome. Thanks a lot. That would be really cool. Thanks.
Hiya. You had a slide showing the rate of failure and the number of GPU failures you had. I'm interested to know, is that 0.6% figure like representative of a normal rate of failure that you'd see in your estate? And also, what kind of things are you counting as failures? How are you tracking them? Is it just like every time a no problem detector check fails, that increments the count?
So the way we do it is when we notice, specifically when we can't run a workload on that node, we've basically identified that the device is that we can't use it. And generally, under the hood, that means that the GPU is falling off the bus. But a lot of times, this is a driver failure that we've encountered because we switched drivers and we're not able to run a workload on it. So that's how we will increase the counter for that metric, is we'll detect that and we can't run a workload on it. So we know we need.
So it's based off of the response from the user's job that they can't run, rather than your metrics you're monitoring on the node.
We have a device plugin that will detect it, because it will try and switch the driver, and when it can't, it will share the metric, and that will get posted as a condition on the node. And then, so your first question about the value of 0.6%. So this is based on the total number of GPUs we have in the fleet. So we have the value that we do over 24 hours, and that's based on the total. So the percentage is based on the number over 24 hours and how much that is of 60,000. And so something to think about with that is, because like we mentioned, reboot, and it's the density, right? There's a sort of another part of this, right? That's just the failure rate, but think about the capacity. The capacity equation gets a little more challenging. You'd have to double it. So 0.6 times 2 would be 1.2 if you wanted to remediate, right? So the failure is 0.6%, but the actual remediation is 1.2%. And if you went up to 8, you'd actually do times 4, right? So now the number gets a little bit more scary. So that's kind of what we were alluding to, is that, and this can also change, like if you're doing cross nodes, right? Like now how do you schedule that? That's a whole scheduling problem that you have to figure out. And when you should, what if your workload demands that it needs an H100 or there's 10 H100s right across? How do you figure that out? Because that might not exist, because you might have 9, right? And you just can't give the 10th. So there's like a few challenges here that just that one number illustrates, and kind of where we want to go with this working group.
Thank you very much.
You're welcome.
Thank you, everyone. If
Thank you.
there are any questions, we can answer them after the talk is over.